Black holes are among the most fascinating objects in the universe. They captivate the imagination of scientists and enthusiasts alike, drawing us into their mysterious depths. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. This immense gravitational pull is a result of their incredible density. Imagine a place where the fabric of space and time is bent to its absolute limit. This bending of space-time is so extreme that it creates a well from which nothing can climb out. This is the essence of a black hole. It's a region where the known laws of physics are pushed to their breaking points. Black holes are not empty spaces. They are incredibly dense concentrations of matter, formed when massive stars collapse under their own gravity. They are incredibly dense concentrations of matter. This density is so extreme that it warps the very fabric of space-time around it. Imagine the mass of several suns squeezed into a region the size of a city. This gives black holes their immense gravitational pull, which is strong enough to trap light. This extreme density creates the immense gravitational pull that defines a black hole. It's a force so powerful that it can distort time and space itself. The boundary of a black hole is called the event horizon. This is the point beyond which nothing can escape the black hole's gravitational grip. Once something crosses this boundary, there's no turning back. The event horizon marks the limit of our observable universe within the black hole. It's a point of no return, even for light itself. This is why black holes appear black. No light can escape to reveal their presence. This makes studying black holes a remarkable challenge, pushing the boundaries of our understanding of the universe. Scientists use advanced technology and theoretical models to unravel the mysteries of these cosmic giants. Observatories around the world, both on Earth and in space, are dedicated to observing black holes. They collect data that helps us understand the behavior and properties of these enigmatic objects. Through simulations and theoretical work, scientists are piecing together the puzzle of how black holes form, evolve, and interact with their surroundings. Each discovery brings us closer to understanding the fundamental nature of our universe. One of the most exciting areas of research is the study of black hole mergers. When two black holes collide, they send ripples through space-time known as gravitational waves. These waves provide a new way to observe and understand the universe. The study of black holes is not just about understanding these mysterious objects themselves, but also about gaining insights into the very fabric of our cosmos. Each discovery opens new doors to the secrets of the universe, inspiring future generations of scientists and explorers. Black holes are not born overnight. They are the result of a long and dramatic process that unfolds over millions, sometimes billions of years. They form through a dramatic process that occurs at the end of a star's life. When a star exhausts its nuclear fuel, it can no longer sustain the nuclear fusion reactions that counteract the force of gravity. When a massive star runs out of fuel, it can no longer support itself against its own gravity. The outer layers of the star begin to collapse inward, causing the core to become increasingly dense and hot. The star collapses under its own weight, imploding in a spectacular explosion called a supernova. This explosion is one of the most energetic events in the universe, releasing more energy in a few seconds than our sun will emit in its entire lifetime. If the core of the collapsed star is massive enough, the gravitational collapse continues, squeezing the matter into an infinitely small point. This process creates an incredibly dense region known as a singularity, where the laws of physics as we know them cease to apply. This point is called a singularity. The singularity is surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. There are different types of black holes, classified by their mass. These include stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes, formed from collapsed stars, are the most common. They typically have masses ranging from a few times to about 20 times the mass of our Sun. Supermassive black holes, millions or billions of times the mass of our Sun, reside at the centers of galaxies. These colossal black holes have a profound influence on the formation and evolution of galaxies. Intermediate mass black holes bridge the gap between these two categories. They are thought to form through the merging of smaller black holes or the collapse of massive star clusters, but their origins are still a topic of active research. Black holes can grow by accreting matter from their surroundings. As matter falls into a black hole, it forms an accretion disk, heating up and emitting intense radiation before crossing the event horizon. Some black holes also produce powerful jets of high-energy particles that shoot out from their poles at nearly the speed of light. These jets can extend for thousands of light years and have significant effects on their environments. When two black holes merge, they create ripples in the fabric of space-time known as gravitational waves. These waves were first detected by the LIGO Observatory in 2015, providing direct evidence of black hole mergers. Black holes are fascinating objects that challenge our understanding of physics and the universe. They are studied using a variety of methods, including observations in different wavelengths of light and simulations based on the principles of general relativity. As we continue to explore the cosmos, black holes remain one of the most intriguing and mysterious phenomena, offering insights into the fundamental nature of space, time, and gravity. The event horizon is the defining feature of a black hole. It's the ultimate cosmic boundary, a point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. Not even light, the fastest thing in the universe, can outrun its grasp. What happens to an object as it approaches a black hole? The immense gravity creates tidal forces that stretch and compress the object, a process known as spaghettification. Imagine a spaceship falling into a black hole. The side of the spaceship closer to the black hole experiences a much stronger gravitational pull than the side farther away. This difference in gravity stretches the spaceship, like spaghetti dough being pulled thin. Eventually, the spaceship would be torn apart, its atoms stretched into a long stream. Section 4. Glowing abyss, accretion disks, and Hawking radiation. These phenomena are among the most fascinating and complex aspects of astrophysics, offering a glimpse into the extreme conditions near black holes. While black holes themselves are invisible, their presence can be inferred by the way they interact with matter around them. The gravitational pull of a black hole is so strong that it affects the motion of nearby stars and gas clouds, creating observable effects. One telltale sign is the presence of an accretion disk. These disks are formed from material that is drawn towards the black hole, spiraling inward due to the immense gravitational forces. As gas and dust fall towards a black hole, they spiral inward, forming a flattened disk of material. This process is not instantaneous. It can take thousands or even millions of years for the material to finally cross the event horizon. The material in the accretion disk heats up due to friction, emitting intense radiation across the electromagnetic spectrum, including visible light, X-rays, and gamma rays. This radiation is a key indicator of the presence of a black hole and provides valuable information about its properties. This radiation allows astronomers to detect and study black holes, even though they cannot see the black holes themselves. By analyzing the radiation emitted by the accretion disk, scientists can determine the mass, spin, and other characteristics of the black hole. Surprisingly, black holes are not entirely black. They emit a faint glow due to a phenomenon known as Hawking radiation. In the 1970s, physicist Stephen Hawking predicted that black holes should emit a faint thermal radiation due to quantum effects near the event horizon. This groundbreaking theory combined principles of quantum mechanics and general relativity, two of the most fundamental theories in physics. This radiation, known as Hawking radiation, is incredibly faint and has not yet been directly observed. However, its existence has profound implications for our understanding of black holes and the nature of the universe. It suggests that black holes can slowly lose mass and energy over time, eventually evaporating completely. The concept of black hole evaporation challenges the traditional view of black holes as eternal objects. Instead, it paints a picture of a dynamic and ever-changing universe, where even the most massive and seemingly permanent structures are subject to the laws of physics. The study of accretion disks and Hawking radiation continues to be a vibrant field of research. Scientists are constantly developing new theories and conducting observations to test these ideas, pushing the boundaries of our knowledge about the cosmos. With the advent of more advanced telescopes and space observatories, we are getting closer to directly observing phenomena like Hawking radiation. These advancements hold the promise of unlocking new secrets about the universe and deepening our understanding of the fundamental forces that govern it. As we continue to explore the mysteries of black holes and their surrounding environments, we are reminded of the vastness and complexity of the universe. Each discovery brings us one step closer to unraveling the secrets of these enigmatic objects and the fundamental nature of reality itself. Section 5. Time's distortion, black holes, and the nature of time. Black holes are not just cosmic vacuum cleaners, they are also cosmic time machines. According to Einstein's theory of general relativity, gravity affects the flow of time. The stronger the gravity, the slower time passes. Near a black hole, where gravity is incredibly strong, time slows down significantly relative to observers farther away. Imagine two identical clocks, one placed near a black hole and the other on Earth. The clock near the black hole would tick much slower than the clock on Earth. If you could observe the clock near the black hole, you would see its hands moving at a snail's pace. This effect, known as time dilation, is a mind-bending consequence of general relativity.